All right, welcome to the deep dive. You know why you're here, right? You want to get to the good stuff, the breakthroughs, without wading through a sea of jargon.
Exactly. Cut to the chase.
And that's exactly what we're doing today. We're talking about a huge leap forward in AI, specifically AI reasoning from Deepseek AI.
Some really interesting stuff.
Yeah, you sent me their research paper on this new Deepseek R1 series of models.
Yes.
And, it's not just an incremental improvement. We're talking about fundamentally different ways to teach large language models to actually, well, think.
That's right. And that's what we're going to unpack today.
Exactly. So our mission, if you will, in this deep dive is to really understand how DeepSeek R1 is approaching this whole challenge of improving reasoning in AI. How are they training these models? What does their, impressive performance tell us about the future of AI? All that good stuff. And we'll try and do it without, melting your brain with too much complexity.
Sounds good.
Let's start with this DeepSeek R10 model. What jumps out at you right away is the way they trained it.
Yeah, it's a unique approach.
It really is.
Really unique.
They decided to train this model purely with reinforcement learning, or RL. And for those who, need a little refresher, RL is kind of like, think of it like training a dog with treats. The AI model tries different things, different actions, and if it gets something right, solves a math problem, writes some good code, it gets a reward.
Right, a virtual pat on the head.
Exactly, which makes it more likely to do that, good thing again in the future. But here's the really interesting bit. They skipped the usual first step of supervised fine-tuning, SFT, where you basically train the model on tons of human-written text so it learns like basic language and context.
It's pretty unusual to jump straight into RL.
It's a bold move.
Yeah, usually models get that initial, grounding in human language before they start learning based on rewards.
Right, exactly. But what's remarkable is that even without that initial SFT, DeepSeek R10 still developed really strong reasoning capabilities.
It did.
Just through this RL process.
It's like, skipping the training wheels and going straight to riding the bike.
Exactly.
And somehow it works.
It's pretty wild. So what we're learning here, I think, is that maybe we don't need those massive, human annotated data sets to teach AI basic reasoning. Maybe we can just focus on, the right reinforcement learning objectives.
Right. And I think that's a key insight from this research. It's not just about the data, it's about how you train the models, how you incentivize the right behaviors.
Absolutely. And when they say strong reasoning, we're not talking about, small improvements. This thing really shines. For example, on the AME 2024, that's the American Invitational Mathematics Examination, it's a notoriously difficult competition. Their initial pass at one score, which basically means getting the first answer correct, was only 15.6%. But after this pure RL training, it jumped up to 71%.
That's a massive improvement.
It is. And get this, with something called majority voting, they even reached 86.7%, which puts it right up there with OpenAI's 010912 model. Yeah, and majority voting basically means they have the model generate like multiple solutions, and then they pick the most frequent one as the final answer.
Ah, so it's like a way to increase their confidence in the results.
Exactly.
Interesting.
So huge gains. And the paper mentions they used this algorithm called Group Relative Policy Optimization, or GRPO.
GRPO, yeah, it's a
Yep.
fascinating approach. It's a way for the model to, essentially learn by comparing its own attempts rather than needing like a separate judge.
So it's like self-critique in a way.
Exactly, yeah. And what's particularly interesting about GRPO is it's very efficient computationally.
How so?
Well, a lot of these, reinforcement learning algorithms, they need a separate critic model to evaluate how good the actions are that the main model takes.
Yeah.
But GRPO, it cleverly sidesteps that. It kind of estimates a baseline directly from, the scores of a group of different outputs that the model itself produces.
Ah, I see. So it's like a more streamlined way of learning.
Exactly. It's a more, self-contained approach.
I got it. So in this whole RL process, what exactly was DeepSeek R10 being rewarded for? What were the, right objectives that we were talking about earlier?
Yeah, so the reward system was pretty clear-cut. It was based on rules, and it mainly focused on two things: accuracy and format. So for accuracy, if the model was doing a math problem, it got a reward for getting the right answer. And if it was doing a coding challenge, they could automatically check if the code actually worked.
Right. That makes sense. And what about the rewards for format?
Yes, so those encouraged the model to structure its reasoning in a very specific way. They had these special tags, think and answer, and they wanted the model to use these tags.
Okay, so think was for like the steps the model was taking to solve the problem, and answer was for the final solution.
Precisely. And this helped the model, clearly separate its thought process from the actual answer. So it made it easier to understand what the model was doing.
It's interesting. They decided to go with this rule-based reward system instead of using what they call neural reward models, which are often used in RL. The paper kind of touches on their reasoning for this.
Yeah, they specifically mentioned that they were a bit wary of reward hacking.
Right. That's where the model, instead of actually getting better at the task, just figures out how to game the system, how to get high rewards without really learning.
Yeah, like a student figuring out how to ace a test without actually understanding the material.
Exactly. And they also pointed out that training these neural reward models can get really complex and computationally expensive.
It's like adding another layer of complexity to the already complex process.
Right. So they wanted to keep things as straightforward and reliable as possible. So how did they actually prompt the model during training? What instructions were they giving it?
The training template was surprisingly simple, actually. It was just a basic instruction, asking the model to produce a reasoning process, and then the answer.
Okay. And of course, using the think and answer tags that we talked about.
Exactly. And the really important point here is that they deliberately didn't give the model any specific guidance on what that reasoning process should look like.
So they weren't feeding it examples of human reasoning or anything like that.
No, they just wanted to see what would emerge naturally through the reinforcement learning process.
Fascinating. And so it was really about letting the AI kind of figure things out on its own.
Exactly. It's like giving the model a sandbox and some tools and seeing what it builds.
Right. And it really ties back to what we were talking about earlier. Instead of focusing on just massive data sets, Deepseek AI is exploring these more targeted training methods.
It's about efficiency, right?
Yeah.
Finding the most effective ways to teach these models.
Exactly. And that's exactly what our listeners are looking for, those efficient ways to get knowledge. And emerge those reasoning skills did. The paper talks about the self-evolution process where, get this, the model's thinking time actually increased as training went on.
Yeah, they were tracking how long it took the model to generate responses, and they noticed that as it got better at handling more complex tasks, it started taking longer.
Like it was pausing to really think things through.
Exactly. It was doing more internal computation.
That's amazing.
It's almost as if it was learning to slow down and really explore the problem before jumping to a conclusion.
And this led to some pretty unexpected reasoning behaviors. Like the model started showing signs of being able to reflect on its own steps and even try different approaches to solving a problem.
Yeah, it wasn't just following a set of rules. It was starting to exhibit a certain level of flexibility and adaptability in its reasoning.
Right. And these weren't behaviors that were explicitly programmed in. These things just emerged organically from the reinforcement learning process.
It's a testament to the power of RL, right?
Hmm.
It's not just about mimicking human behavior. It's about allowing the AI to develop its own unique problem-solving strategies.
Exactly. And that's what makes this so exciting. And then there's this, what the paper calls the aha moment, which I found particularly striking. It's documented in Table 3, where one of the intermediate versions of the model does something completely unexpected.
Yeah, this was wild. So this model, it was working on a math problem, and it actually generated a thought that was almost like, an internal monologue. It said, wait, wait, wait. And then it went back and reevaluated its solution.
It's like it suddenly realized it was on the wrong track.
Yeah, it was like a moment of self-correction, a realization that, hey, maybe I need to approach this differently.
It's amazing. And this wasn't programmed in. It just emerged from the learning process.
It speaks to the potential of RL to lead to these, emergent, seemingly insightful behaviors.
It really does. However, this initial approach with DeepSeek R10 wasn't without its limitations, and the researchers identified a couple of key areas for improvement.
Right, because it wasn't initially trained on, curated human reasoning data. The language it used could sometimes be a bit unclear, or even mix different languages within its reasoning process.
Which, if you're trying to understand the model's logic, it can be pretty confusing.
Exactly.
So that brings us to DeepSeek R1, which seems to build on those valuable lessons they learned from the 0 version.
Yeah, they made some key changes to the training process.
Right. So what's the main difference here?
Well, the biggest one is that they introduced this cold start phase.
A cold start.
Yeah, where they basically fine-tuned the base model with a small amount of really high-quality data before they started the reinforcement learning.
Okay, so why the change? Why add this extra data step? Was it, something they saw in the Deepseek R10 results that made them think, okay, we need to do this?
There were a couple of main reasons, actually. Firstly, that initial phase of pure RL with Deepseek R10, it could be a bit unstable. So starting with some well-chosen examples, it kind of helps to create a more stable foundation for the subsequent learning.
Right, kind of like giving it a head start.
Exactly. And the second reason was they wanted to create a model that was more user-friendly, one that produced clearer reasoning that's easier for us humans to understand.
Makes sense. So where did they get this cold start data from?
They used a combination of techniques. They did some few-shot prompting, where they gave the model just a few examples of good reasoning. And they also did some direct prompting, where they asked models to generate, very detailed answers that included reflection on their own thought processes.
So they were basically trying to elicit those, human-like reasoning patterns from the models themselves.
Exactly.
Hmm.
And they also took some of the outputs that were generated by Deepseek R10, and they cleaned them up and made them more readable and structured. And finally, they had human annotators review and improve the overall quality of this initial data set.
So a lot of effort went into creating this high-quality cold start data.
Yeah, they wanted to make sure it was really good.
And what were the tangible benefits that they saw from this?
Well, the biggest one was that the readability of the model's output improved significantly.
Which was one of the issues with DeepSeek R10.
Exactly. And they also believe that this initial guidance, this grounding in human-like reasoning, could potentially lead to even better performance overall.
Interesting. And they actually designed like a more structured output format for DeepSeek R1, right?
They did, yeah. They started using these special tokens to clearly separate the detailed reasoning steps from the final summary of the solution. So it was like, special token reasoning process, special token summary.
Right, so it's much clearer what's what. And that's definitely more practical for real-world applications. Okay, so we've got the cold start. We've got this initial fine-tuning. What happens next in the training of DeepSeek R1?
So after the cold start, they moved into a reinforcement learning phase, specifically focused on reasoning. And this was similar in principle to what they did with Deepseek R10. The goal was to further improve the model's abilities in those challenging areas like math and coding.
Right, to really push the boundaries of its reasoning capabilities.
Exactly. But they still noticed some instances of, language mixing happening within the model's thought processes. So they decided to introduce an extra reward signal to address this.
What did that reward do?
It was a language consistency reward. Basically, they calculated it based on the proportion of words in the model's reasoning that belonged to the desired target language.
So the more consistent the language, the higher the reward.
Exactly. And they found that while this might have, in some cases slightly impacted the raw performance scores on certain benchmarks, it led to a much bigger improvement in the readability and coherence of the reasoning.
And that's what matters, right? You want the model's reasoning to be clear and understandable.
Exactly. It needs to make sense to humans.
So they've done the cold start, they've done the reasoning focus RL, all while making sure the language is consistent. What's the next stage?
Right. So the next crucial step was rejection sampling and supervised fine-tuning, which is often shortened to SFT.
SFT. Got it.
And this stage involved two main types of data: reasoning data and non-reasoning data.
Okay, let's break that down. What's the reasoning data?
For the reasoning data, they took the best performing model from that reasoning-focused RL phase and generated a much larger data set by doing something called rejection sampling. So basically, the model would generate a bunch of different responses, and they would only keep the ones that met certain quality criteria.
Ah, so they were really filtering out the less desirable outputs.
Exactly. They were being very selective. And interestingly, they also used a generative reward model, Deepseek V3, to help them evaluate the quality of these reasoning steps.
So they were incorporating another model into the process.
Yeah, and this allowed them to include a wider range of data than what they could evaluate with just simple rules.
Makes sense. And they were also filtering out, those problematic outputs, like the ones with mixed languages or really long chunks of text.
Exactly. Anything that wasn't up to par.
Right. And this process gave them around 600,000 really high-quality reasoning examples.
Impressive, right?
It is. So that's the reasoning data. What about the non-reasoning data? Why was that included in this SFT stage?
Well, they wanted to make sure that Deepseek R1 wasn't just good at reasoning, but also had strong general capabilities. Things like writing, answering questions, self-awareness, translation.
Right, so it's a more well-rounded AI.
Exactly. And for this, they actually reused portions of DeepSeek V3's existing SFT dataset, which had about 200,000 samples covering those diverse skills.
Ah, so they're leveraging the work they've already done with Deepseek V3.
Exactly. It's all about efficiency.
Right. And then they fine-tuned the base Deepseek V3 model using this combined data set of about 800,000 samples.
That's a lot of data.
It is. So we've got the cold start, we've got the reasoning-focused RL, we've got the SFT with both reasoning and non-reasoning data. What's left?
Well, there's one final stage, and that's reinforcement learning for all scenarios.
So more RL, but this time it's not just focused on reasoning.
Exactly. The focus here shifts to making sure the model is helpful and harmless.
Right, because those are, crucial considerations for any AI system.
Absolutely, especially as these models become more powerful.
So how did they approach this final RL stage?
For the reasoning data, they went back to using those rule-based rewards, like they did in DeepSeek R10. But for the general data, they used reward models to evaluate the helpfulness and harmlessness.
Okay, so different approaches for different types of data.
Right. And they actually focused on different parts of the model's output for these different evaluations. For helpfulness, they mainly looked at the final summary the model generated, how concise and informative it was. But for harmlessness, they looked at the entire response, including all the reasoning steps.
So they were being very thorough.
They were. And this incredibly detailed training process, it really paid off. The performance of DeepSeek R1 is really impressive. It's right up there with some of the most advanced models out there.
And all this leads us to another fascinating aspect of their work. They were able to transfer these reasoning abilities to smaller, more efficient AI models using a process called distillation.
Yeah, distillation is a really powerful technique.
And what exactly does it involve?
So basically, you take all that knowledge, all those reasoning patterns that the larger, more capable model has learned, and you transfer them to smaller models.
So it's like a teacher-student relationship.
Exactly. And in this case, the teacher was DeepSeek R1, and the students were models from the Quinn and Llama series, which are generally smaller and more efficient.
Right. And they did this transfer using more supervised fine-tuning, right?
That's right. They fine-tuned the smaller models using that same high-quality data set of 800,000 samples that they used for DeepSeek R1.
And the really amazing thing is that this distillation process actually worked. It significantly boosted the reasoning abilities of these smaller models.
It did.
And this is a really big deal because it means that we don't necessarily need those, massive resource-intensive models to get good reasoning.
Exactly. We can take the knowledge from the big models and transfer it to smaller, more accessible models.
Right, which is great news for, people who want to use these models but don't have access to those huge computing resources.
It democratizes access to advanced AI in a way.
And the results are pretty compelling. Their 7 billion parameter DeepSeek R17B model, it actually outperformed GPT-4o0513 on several benchmark tests. And their 14B model, it beat QWQ32B preview on every single metric. And then their larger distilled models, the 32B and 70B versions, those perform significantly better than O1 Mini on most of the reasoning benchmarks.
So even those smaller models are packing a punch.
They really are. And they didn't even use RL for these distilled models.
Right. They wanted to show that distillation alone was enough to achieve these significant improvements.
Which means there's even more room for improvement.
Exactly. They think that if they added an RL stage for these distilled models, they could probably push the performance even further.
So lots of exciting possibilities there.
Yeah, lots to explore.
Now, the paper also talks about some of the things they tried that didn't work, which I think is just as valuable as knowing what did work.
It is. It shows that, progress isn't always linear. There are bumps along the way.
Exactly. So they have a section called Unsuccessful Attempts. And one of the approaches they tried was the Process Reward Model, or PRM.
PRM.
Yeah. What were the issues they ran into with that?
Well, the main challenge was that it was really hard to define, clear, granular steps that would apply across different types of reasoning tasks, like what counts as a good reasoning step. It's not always obvious.
Right, especially when you're dealing with complex problems.
Exactly. And it was also difficult to automatically figure out whether each step was correct. They could have done it manually, but that wouldn't be scalable. They couldn't do that for every single step of every single problem.
Right, it would just be too much.
And then, of course, there was the risk of reward hacking, where the model learns to manipulate the system instead of actually improving its reasoning.
So they found that PRM wasn't really that helpful for their large-scale RL training.
Right. They said it might be useful for things like re-ranking responses or guiding the search process, but not so much for actually improving the model's reasoning abilities.
Okay, interesting. And the other thing they tried that didn't quite pan out was Monte Carlo tree search, or MCTS.
MCTS, yeah, that's a technique that's been really successful in games like Go.
Right.
But they ran into some challenges when they tried to apply it to language models.
What were the challenges?
Well, one of the biggest ones was that the search space for generating text is just vastly larger than the search space for games like chess or Go.
Because with text, you have like an almost infinite number of possible words and phrases you can choose from.
Exactly. And that makes it much harder to explore the space effectively. And then they also had trouble training a good value model to guide the search process. So it wasn't as effective as they were hoping it would be.
So MCTS, while promising in theory, wasn't really a viable solution for their training setup.
Right, at least not yet.
So to sum up what we've learned about Deepseek R1, we saw that Deepseek R10 showed us that you can get good reasoning purely through reinforcement learning. Then Deepseek R1 built on that with the cold start and the multi-stage training process.
Right, and ultimately achieving performance that's comparable to some of the leading models out there.
Exactly. And they also showed us that we can transfer these reasoning abilities to smaller models through distillation.
Which is a really exciting finding.
It is. And, I keep thinking back to that aha moment we talked about with Deepseek R10. It's just mind-blowing that these, seemingly insightful behaviors can emerge from just reinforcement learning.
It is.
It makes you wonder what other cognitive skills we might be able to unlock with the right training methods.
Right, if we could figure out the right incentives and the right frameworks, who knows what's possible?
Absolutely. And the paper mentions some interesting future directions for Deepseek R1.
Yeah, they have lots of ideas they want to explore.
Like what?
Well, they want to work on improving the model's general capabilities, things like function calling and multi-turn conversations.
So making it more versatile and interactive.
Exactly. And they also want to address that issue of language mixing that they observed, and they want to better understand how sensitive the model is to different ways of prompting it. And finally, they're going to focus on improving its performance on software engineering tasks.
Really interesting stuff. So as we wrap up this deep dive into Deepseek R1, it leaves us with a really intriguing question. If Deepseek R10 was able to develop such impressive reasoning abilities without any initial human examples, what other complex cognitive skills could we see emerge in AI systems if we just figure out the right ways to train them?
It's a great question.
It really is. It's something for all of us to think about as we continue to explore the world of AI. So thanks for joining me on this deep dive.
My pleasure.
It's been a fascinating conversation. Until next time.
See you then.